Good afternoon. Thanks for your time. I want to talk about a new product that we brought to the market around about 2.5 years ago, and is now being distributed around Europe at the moment with plans to take it further afield. The basic concept here is simplicity, and one of the main issues that we want to address is the use of compressor cooling in data centers. We don't feel that there's a real need to use compressors anymore. So we want to see data centers move towards 100% free cooling, which we can achieve throughout most of Europe certainly, and further afield. It's a very rare thing that we can provide a product which is not only lower cost, but it also has increased efficiency and increased reliability. Normally you don't get all of those together at once. You can have one of two or two of three, but not all of them. So just to begin with where we're at right now, typical PUEs in the data center market are around about 2. And of that, around about a quarter of that is built up of cooling. So for every kilowatt of power you deliver to the space, you're using about half a kilowatt just to cool it down. So your IT power needs half as much again to cool it down. Now, we want to eliminate that as much as possible, and in the data centers that we are working on today, several in this country and others throughout the rest of Europe, we're achieving PUEs that are far lower than 2. And the main reason for doing that is because we're using outdoor air as a cooling medium. We're only pushing air around the space, and we're removing the need for compressors throughout all of those. As I say, the solution to reducing your PUE and increasing your reliability is to remove or reduce your dependency on mechanical cooling. Typically in the data centers that we're working on, we're seeing PUEs, calculated PUEs now of 1.15. And in terms of that chart that we just put up there before for the PUE of 2, we're seeing only a small chunk of that power is required for cooling. So we're releasing that stranded power now back to the operator, who can then deploy that power for what is really the purpose of the data center, and that is for IT processing. We do that in a fairly, was unique 3 years ago, but there's a few competitors coming to the market now. We do that in a fairly unique way in that we use an indirect system for cooling. So we're using outdoor air as a cooling medium, but we're not introducing that outdoor air into the space. Really, really important that you get that in your head, because as soon as you start introducing outdoor air into the space, you bring the compressors back into the system, because you cannot rely on outdoor air all year round. No matter who you are or what you're doing, if you're bringing outdoor air into the space, there's a chance that there might be a poor air quality, such as a fire, which means you need compressors. So we use outdoor air purely as a cooling medium. Now, in the winter, when the outdoor air temperature might be at 10 degrees C, that's a fairly straightforward thing to do. We're passing air through one side of a heat exchanger, and we're using that to remove the heat from the data center on the other side of that heat exchanger. The two air streams never meet. In the middle of summer, when things get a little bit warmer and it gets a bit more difficult to achieve that, we introduce our adiabatic and evaporative system, which introduces moisture into the outdoor air stream only. That has the effect of lowering the outdoor air temperature from its dry bulb temperature to its wet bulb temperature, which generally speaking in the UK, for instance, will reduce the temperature from 35 degrees C down to maybe 21 degrees C. And it's that we use as a cooling medium to introduce air into the data center within the ASHRAE TC 9.9 recommended environmental envelope. Typical arrangement is the Excool units are large air handling units which are attached to the outside of the building, introducing air directly into the space or recirculating air directly from the space. This is a project that we've just supplied to Digital Realty in Profile Park in Dublin. And this is the basics of what's going on inside the box. I haven't got a pointer, unfortunately, so you'll have to bear with me, but we're taking return air back from the space. We're passing it through one side of a heat exchanger and delivering it back into the space. The external air is being drawn through the other side of the heat exchanger and then discharged to atmosphere. So the heat is basically being removed from the data center and discharged to atmosphere via a heat exchanger. And that is the only heat transfer that we have in the entire system. Okay, and that's winter operation. In summer, we add moisture to the outdoor airstream to reduce that temperature down. That allows us to supply air at 24 degrees C all year round, providing the wet bulb temperature remains at typical UK conditions. In the middle of, let's say, the south of France, or where we have a client that wants a very low supply temperature, we can introduce a top-up DX section. And that there is only, it would normally only be around about 25% of the total cooling load, and is there to provide top-up cooling in the middle of summer for a few hours per year. The dreaded psychometric chart, but I need this just to describe to you exactly what's going on. Typically in the UK, we would be here. We would be at 35 degrees C and around about 25% relative humidity on a peak summer day. To that we add moisture. By adding moisture, that takes us up the wet bulb line, increasing the humidity to 100%. We effectively now have lowered the outdoor air temperature from 35 degrees C to 21 degrees C simply by adding moisture. And it's this that we use as a cooling medium. Now, if we're trying to achieve supply conditions in line with ASHRAE recommended envelope, providing our outdoor air condition remains in this blue zone, we do not need to provide mechanical cooling. So that's our outdoor air condition anywhere in that blue zone. So you can see that we can be as hot as 50 degrees C externally, providing the outdoor air humidity is relatively low. And this is where it gets really interesting. If we have clients that are prepared to operate up to the ASHRAE allowable A1 class range, which allows air to be supplied at 32 degrees C for a few hours per year, then suddenly that zone increases to that point there. Now, there's very few places in the world that exceed those outdoor air conditions. That's demonstrated on this map of the world, which is a wet bulb temperature map, which is completely different to what you'd expect to see if it was a dry bulb temperature map. And you can see there that we're able to operate Excool in the middle of the Sahara Desert without any compressors. We need a fair bit of water to do that, admittedly, during the summer, which is pretty much all the year, but we don't need compressors. Now in the UK, we are now supplying probably around about approaching 60 megawatts worth of cooling without any compressors at all in Europe. You can see there in places like Madrid, for instance, you're able to supply air for most of the year without any mechanical cooling at all. So this is what a wet bulb temperature gradient looks like for London, for Heathrow Airport. The wet bulb temperature rises to around about 22.5 degrees C on a peak day. For us to maintain 24 degrees C supply, which is generally where most of our clients want to sit, we would need to introduce moisture to the outdoor airstream on where that blue line crosses the temperature gradient. So around about 15.5 degrees C dry bulb, we start to introduce moisture. The compressors would be needed to maintain 24, remember, at this point here. So you can see the area that's left under that graph is very, very small. It's a couple of hours a year to maintain 24 degrees C. What most of our clients are saying is that I'm not going to put compressors in there, even if it may only be 25% of the total load. I'm still not going to use compressors for those 2 hours per year. I'm just going to go to allow the temperature to rise above 24 degrees C, maybe up to 26 degrees C for maybe 2 hours a year. And by doing that, I avoid the need for compressors. So he needs to rewrite the standard service level agreement to accommodate that. So I want to talk about PUEs. It's a pet hate of mine, but it's quite a useful metric to use, as most of you in this room will understand it. I think it's a bit flawed, but it's something that the whole industry understands. But what I want to talk about is partial PUE. So the PUE that applies only to the cooling section of the calculation. And typically with a free cooling chiller system, which is a sort of system of choice up until very recently, a chiller system would have a partial PUE at best of around about 1.2. These are the sort of PUE levels that we get with Excool. So we're down at around about 1.03 or lower throughout most of Europe. And what this table is also showing you is the number of hours that we need to run compressors to maintain 27 degrees C as an upper limit in the recommended column, or 32 degrees C as an upper limit in the allowable column. There's some real surprises up there. Places like Riyadh, yes, we do need compressors to maintain ASHRAE recommended, but they only run for 4 hours per year. Certainly in London, we don't need any compressors at all. So it's all fans and pumps is all we need to cool the data center down. One of the products that has been favoured in certain regions over chill water and has produced some really low PUEs is direct air systems. The problem we have with direct air systems, or our clients have with direct air systems, is a contamination risk from poor air quality. A simple car fire or a forest fire or a building fire local to your site, or bonfire night in this country on the 5th of November will produce smoke locally, which will be taken into the data centre. Therefore, you need to shut the outdoor air down and recirculate all of your air within that space, therefore needing full compressor backup to maintain conditions. This is where it gets quite interesting as well. We've got psychometric chart here. The blue zone is the recommended envelope recommended by ASHRAE. To maintain those conditions, you would need to, if the outdoor air condition is within the zone that's just gone up on the screen there, you'll need mechanical cooling and dehumidification. Some choose to ignore that and allow humidity to rise in the space, which can result in condensation on the racks. But more importantly, it's the winter operation. Humidity drops in the winter if you're bringing outdoor air in rather dramatically, particularly in the middle of winter when it's below zero outside. So you need to introduce moisture into that outdoor air stream, and that's normally done with electrode boiler humidifiers. So you're basically boiling big kettles to introduce steam into the data center to maintain humidity. So huge amounts of energy required to do that. And this is in more extreme and more polluted regions around the world, particularly, but also in city centres where you have a high concentration of sulphur in the atmosphere. We are seeing an increased level of corrosion on the server boards themselves, caused by copper creep and silver whiskers, where the printed circuits on the boards themselves tend to break down through corrosion. So this illustrates what I'm trying to get across, is that if you've got a traditional chill water or direct air system, you're going to need a full mechanical cooling backup. If you're in Madrid, you're only going to need 25% top up, and that will only run for 4 hours of the year to maintain 27 degrees C as a peak temperature. In London, no cooling is required at all, mechanical cooling. So it's 100% free cooling, but it's 100% mechanical free cooling. I want to stress that. So it's compressor free cooling. There's no such thing as free cooling. What this also, the impact that this also has on your infrastructure is that you can reduce the cost of your electrical infrastructure significantly. Our clients are reporting a 25% saving on their electrical infrastructure costs because they're making significant savings on their generators, transformers, and switchgear, diesel storage, etc., etc. So in terms of capital cost, I did begin this by saying that it's actually lower cost in the first place, lower energy and higher resilience. This demonstrates those costs, and these are fairly accurate based on feedback we've had from clients that have traditionally used chilled water. What we find is that the cost of the Excool unit and the water storage that is required for the Excool unit matches the cost of the basic mechanical cooling infrastructure. But there are significant savings to be made on the electrical infrastructure and the water storage, which is shown or represented by this graph that I've got up on the screen now. It's a typical 1 megawatt data centre, M+1 in London. But this is where the real savings are, is in running costs. Our running costs are around about 10% or lower than that of a traditional chill water system. And our maintenance costs, because we're only talking about a bunch of fans and pumps here and some filters to maintain, our maintenance costs are minuscule. Most of the maintenance can be done by trained operatives on site. We're talking about filter changes, and that's really about all you've got to worry about. We would need our engineers on site maybe once or twice a year to calibrate controls. As soon as you start spraying water, the question is always asked, questions are always asked surrounding Legionnaire's disease and bacterial control. And one of the things we decided to do very early on was design out the propensity for bacteria to grow. So we don't harbour any bacteria within the unit. We drain it down after each day. We purge the system if we haven't used it for more than a day. So we allow water to flow before we actually bring the sprays on. We also have a biological filter built in, which is a 0.2 micron filter, which will filter out bacteria, which is 0.6 micron. And we have an anti-scale system, which prevents scale building up within the unit, which is a food source for bacteria, but is also quite detrimental to the performance of the unit. In terms of water quantity, it's fairly small as well. We're only using around about 1,500 cubic meters per annum, which is the equivalent of around 30 people's domestic use per megawatt of cooling. In terms of process cooling, it's a drop in the ocean, excuse the pun. Frost control, we don't need to worry about frost control in the middle of winter because we're not spraying water in the middle of winter. The system is dry. The one thing that does need to be considered here is water storage. In areas where you may have two completely separate water supplies, you don't need to worry about water storage. That's a real luxury, and there aren't many places in the world that have that. So we need to consider burying or storing and keeping cool a store of water. Because if we lose the water supply, then quite clearly we lose the cooling ability in the middle of summer. So in terms of maintenance, I touched on this earlier on. We have a basic maintenance regime, which is to inspect and clean water filters and air filters at regular intervals, and that can be done by site-based engineers. Controls, we will come to site and calibrate and test those once or twice a year. The plate heat exchangers themselves are self-cleaning because we're spraying water on them regularly in the summer, but they can be flushed if they do get contaminated. We can't imagine how they would do, but they can be pressure washed because they're made of a very robust material. And the fans and motors, they're sealed for life bearings, which have a lifespan of between 5 and 10 years, running at 45 degrees C ambient and 100% fan speed. We don't get anywhere near that for any time at all. So the likelihood is that fans and bearings will last for the life of the machine or the life of the data center. But we do monitor the temperature of the bearings and the temperature of the windings remotely for you and issue reports to make sure that we're maintaining healthy conditions on all of those fans and motors. So just in summary, to conclude what I've just been talking about, there's a lower total cost of ownership with this product. You've got reduced capital expenditure, reduced operating expenditure, reduced maintenance costs, reduced infrastructure costs. Your building can be smaller because you've taken the crack units out of the space now. Invariably, what tends to happen is people put more because there's more power available, people put more racks into the space. And you can reduce your build costs. You could build a smaller data center because you don't need space for the internal cooling equipment. Again, most people will stick with the same size data center and put more racks in and get more IT out of it. In terms of operational improvements, there's an increase in available IT power, improved resilience. Again, it's a bunch of fans and pumps. If we lose one of these fans, you generally would go N+1 as a minimum. But if we lose one fan on a large unit, we've lost 1/16 of its cooling capacity on one unit. Same with the pumps. We have 4 pumps on each of the units. So if we lose one pump, we lose 25% of the cooling ability of that one unit. And all that simply happens is an alarm is raised and the other units increase their speed marginally to accommodate it. We also would get across to you that there's a faster return on investment when you're comparing this with a chilled water system. If you've got a 4 megawatt deployment, let's say, with a chilled water system, you're going to need to put in your chilled water system, your chillers, your pipes, your pumps, everything else for that 4 megawatts, and then may only deploy 200 kilowatts of IT to begin with. So you may only put in a small number of crack units, but you've got your basic infrastructure in place day one. With Excool, you can install Excool units to match your IT growth.